And the rest you call Z. And that's an accepting state, so that's why I put a double circle in. Let y be equal to ci plus 1. So from here to here, ci plus 1, ci plus 2, ci plus 3, etc. up to cj minus 1. Cj from here to here. So that will be cj. And then this will be cj plus 1. And so let me just clean up some of this mess here. Now, I probably should put in some arrows because, you know, you need these arrows. Arrow here and arrow here. Now, let x be equal to this, y be equal to this, and z be equal to this. Then we can see that for each r greater than or equal to 0, x, y, z, x, y to the r will be accepted by my. You go here, you do this thing r times, including r equals 0, and then you come out, and then you reach an accepting thing, so it's an acceptance track. Okay, you start here, and you ended up here. So you go, okay. And now, because r is taking the value 0, 1, 2, you'll get an infinite number of strings. So all these strings will be different because the y is not lambda. If the y was lambda, then, you know, that's why we needed this lambda free. Where is the word? Lambda free. Because if you had lambda to this 1, lambda to the 2, lambda to the 100, they're all lambda. But not, you know, as soon as you get one on empty string, you can keep going. So, this thing is blocking my time. Okay, 2:36. Okay, so now we got that going. So we say, okay, since each one of this is different because they are getting longer and longer, x, y to the r, z. So when y is equal, r is equal to 0 is the shortest, it's just xz. And then r is equal to 1, r equal to 2, it keeps increasing by size. Then you get an infinite number of strings, right? And therefore, L of m will be infinite. So you say, okay, I got this guy proved that if you do accept something in that range, then you're infinite. Now, so you're thinking, okay, if you're infinite, you got to accept some long strings. And long means greater than or equal to n. Because all the strings less than or equal to n minus 1, those will be paths maybe, right? By the way, you could have string of length 1 and it is not a path, right? So you're thinking how? Well, you're thinking, okay, if you have a string of length 2, it will be like this and like this, right? You have string of length 1, yes, you could have a, right, you'll be like that. But you could have string of length 1 like this. You start here, and then you go wrong. You're thinking, oh, you can even have a path, you know, that's not a path, but it's an acceptance track of length 1, and it has a loop. But the whole idea is, you know that you want a loop, a big loop, that's greater than or equal to n, right? Now, if phi1 is less than or equal to n2 n minus 1, then take phi naught to be phi1. Remember, what do we want here? We want to say, suppose it's infinite, then this is true. So we want to find that phi naught, right? That idea. So let me take this out. Okay, so we want to find that guy. So now if phi1 is less than or equal to 2n minus 1, then you take phi naught to be phi1, and m will accept a string phi naught with this, right? If phi1 is greater than 2n minus 1, then consider any acceptance track of phi1. And then what you do now, if we dilute the loops in this acceptance track of phi1 one at a time, we will eventually get this string phi naught, which is accepted by m and will satisfy this condition. So m will accept a string in this range. You're thinking, well, no, professor, I don't believe, you know, because you are just saying it, you're making it up. No. Okay, here is strings of length 0, right? String of length n minus 1. String of length n. And then string of length, you know, you just got some string here. And you want to say this is between n and 2n minus 1. So I will take another color. I'm sorry about that. I know I was coming down with something. So this is your phi 1. You start with your phi 1. Right? And then you say, hey, look at the acceptance track and see if it has a loop. Now, in every time you take a loop, you're knocking out. The most you can knock out of a loop is N. So you keep knocking out. You knock out. And then sooner or later, now here is the important part. And this is what, the students cannot see sometimes. You're like, okay, sooner or later, you're going to end up in here. Why? Because you cannot jump from 2N to N minus 1 or less. Or jump all the way there or whatever. You cannot do that. Because from 2N to N minus 1, that is N plus 1. And you cannot jump by more than N. So if you're 2N, the biggest you can jump is an N, and then you'll end up right here. And you're like, okay, I got you. Or if you jump a little smaller, but, so you cannot say, I will not, I can avoid this whole group of N things. You cannot jump from outside here to outside here. It's impossible. So you're thinking, okay. So that's why you keep deleting one loop at a time, and sooner or later you will end up in here. And once you end up in here, that's what the theorem wants. It says, we can end up in between 2N minus 1 and N in length. And that's something that has a range of N possibilities. N plus 0, N plus 1, up to N plus N minus 1. And then you're like, okay. So that proves that result. So this is done. And now I wanted to go and say, okay, proof of the theorem 9, I already proved this, right? Now, the second part. I want to show that if L1, this term is L1 subset of L2. Now, this is an easy thing. This follows from part A. So you're thinking, how? L1 is subset of L2 if and only if L1 minus L2 is empty. You're thinking, wait. Draw some picture for me. So you say, okay, if you are L1 and you want to know if this guy, L1 is subset of L2. So that means if this is L1 and this is L2, right? The only way for L1 to be a subset of L2 is for L1, this minus this is equal to empty. And you're thinking, you're right, because if L1 minus L2 is not empty, L1 is not subset. So you're thinking, this is discrete math. Yeah. And so since L1 minus L2 is a regular language, by theorem 6F, we can follow the algorithm party and check if L1. So it's a regular language. We can check if this is so you get a machine for it, if you get a DFE. And so you convert L1 minus L2 into a DFE. And then you're thinking, okay, and what do you do now? And then we again run the algorithm party. Hey, can you check if this thing is empty or not? If it's empty, then you say yes, L1 is subset of L2. And if it's not empty, then you say, hey, my friend, L1 is not subset of L2. And that's it. So you're thinking, okay, I got that. And it came free from this. Now I switch back to red because I want to show contrast, right? So I want to now determine how can I find an algorithm to show that L1 is equal to L2. Now, these are, to you, you might think, Professor, who cares if L1 is equal to L2? No, it is important because we are looking at simple things. We are not looking at, sort of like climate change and fixing the, the carbon emissions. And these are all very complicated things, climate change and fixing the sea and taking care of all the resources on Earth and, contamination and eliminating problems, saving the world from hunger and controlling the population. All of these things are terrible hard. But they're fine. They can be done, but people keep fighting. But this is computer easy. So you're thinking, so that's why you do the easy problems and leave the hard problem like, saving work or world peace to, the crazy guys. Why don't you guys do, save the world or bring world peace? Well, that's because we don't have the power. So Otherwise, we'll put it in a computer and they'll tell us what to do, but nobody will want to do what the computer says. So observe that L1 is equal to L2 if and only if L1 is subset of L2 and L2 is subset of L1. So you're thinking, okay. So we use the algorithm part B twice to check if this is true. So we have an algorithm to check if this is true. And then you check if the opposite is true. And then if they're both true, you say L1 is equal to L2. If they're not both true, you say, okay, L1 is not equal to L2. So a machine can tell all of these things. You're thinking, man, that machine is good. It doesn't do proofs, but it checks if two things are equal, even though you give too complicated description. Like you could give L1 as a right linear grammar. You could give L2 as a regular expression. And you're thinking, is this right linear grammar guy equivalent to this regular expression? And yes, there's an algorithm, you just feed it in. And what does the thing do? It converts, the language, and then it finds L1 minus L2, find a machine for that, and then check the machine if it has got a, accept a string between the range 0 and n minus 1, where capital N minus 1 is the number of states in the machine. You're thinking, okay, this guy is ready, he's good. So we got that. And then the last thing is what you would like to do is here. You have want to know is L1 infinite. So first you find a lambda free and FEM1. So that this is true, right? And then you say L of M1 is infinite if and only if M1 accepts a string in this range. You're thinking, Professor, I am a little bit confused. Could your M1 be DFA? Sure, if you want, it could be DFA, right? But, it's always better to talk in terms of lambda free and FE because those are more user-friendly. DFA are too rigid. But as long as you accept a string in this range, then you are guaranteed to have a loop. And then once you write that loop an infinite number of times, you're guaranteed to have an infinite number of strings accepted. And so the idea is, how do you know if it accepts something in this range? Well, you're going to check all possible acceptance tracks with length between 2n and 2n minus 1 inclusive. And then if one track works, then you know L of M1 equals L1 will be infinite. If none works, then you know, okay, it will not be infinite. You're thinking, it could have been big and finite, but it's not infinite. And so that brings us to the closure of these things. Now, here comes the hard part. So far, we have been doing all kinds of crazy things, regular grammar, regular expression. Then we went, that's the first chapter, languages and regular expression. You're thinking, I hate regular expression, but they're not so bad. Yeah, it's okay. And then grammar, right linear grammar, you're thinking, I also hated right linear grammar, but context-free grammar were more complicated. But I don't mind context-free grammar and right linear grammars. Right linear grammars are actually easier. So I think I like grammars more than regular expression. Some people like regular expressions more. And then you come to this machine, NFA and DFA. So some people like DFA. Why? Because the DFA is very deterministic. It tells you exactly what is happening. Some people like NFAs. Why? Because it's user-friendly. So that's the two worlds. Some people like user-friendliness. Some people like rigidity. And I'm thinking you got to compromise. You got to have a little bit of both, right? Otherwise, you won't get good programming languages. And so these are the things that tells us, even before there was programming languages, these things were known because these things were known since 1936. And you're thinking, oh, shucks, these guys knew this since 36 and there was no computer yet. Who was the crazy guy? Turing and Gödel and Kleene Star guy. And you're thinking, man, those guys were advanced. Yes. So our goal here is to now talk about non-regular languages. So what does this mean? Well, the first thing you got to remember is that first time you saw proof by contradiction, you saw this fellow, no? You're thinking, yeah, I hate that proof, I still hate it now. Well, no, you can't think like that. That was an amazing idea the Greeks had to say that square root of 2 is not rational. So it cannot be expressed in the form P upon Q. And we got it by proof by contradiction. So you're thinking, yeah, but what does that do? Well, it just tells you that, there is no periodicity of the decimal expansion of 2. And in fact, nobody has found that pattern that is in the decimal expansion of 2. There is no pattern. I mean, there could be a pattern, right? But okay, let me give you an example. Square root of 2 is irrational, right? And so any number that is rational, after a time, it repeats. Like, 1/3, 0.3333, right? 0.5, 1/5, 0.2000. So the zeros repeat. After time, you get a repetition. Then you're thinking, okay, how about 1/7? If 1/7 was a bad guy, he repeats after 7 decimals. You're thinking, oh, shucks. Sorry, after 6. So you're thinking, man, I hate 1/7. But whatever it is, right? 1/7 works, right? And then, you're thinking, okay, every rational number, 73/87 or 5,332/69, all of those will be repeating decimals because they are rational. But square root of 2 is not rational, and so it cannot be a repeating decimal from some point onwards, right? And in fact, there is no pattern. We cannot discern a pattern, right? Now, does that mean you cannot compute square root of 2? No, that's a different story. We'll talk more about that later. But I only brought up square root of 2 to say the set of all regular languages is countable, and consequently, non-regular language exists. That's the first thing. So somebody, like, this is what Cantor did. Cantor said, the set of all real numbers is uncountable. And that's his diagonal argument. And he got approved by contradiction. And then he says, okay, the set of rational numbers is countable. And that means there exists uncountable, there exists a number which is not rational, a real number. But people knew already that square root of 2. So they actually have a concrete example. So this proposition 12 is saying something similar to what Cantor did. Cantor said, hey, so we know the set of all regular languages is countable and the set of all languages is uncountable. Consequently, non-regular languages exist, right? So let us look at this thing here a little bit. We know that a regular language is one that can be described by a regular expression on AB. Now, a regular expression in AB is just a string based on this alphabet. You have A, B, lambda, empty set, plus, dot, star, left parentheses, right parentheses, and then you're like, okay, since the set of all strings based on T is countable, it follows that the set of all regular expression is countable. And you're thinking, okay. And then, not every string will produce a regular expression. Some are just meaningless, like AB star, that's nothing. AB star is, if you write something like A and then you write a B, right? Or you write star AB, put it that way. You're like, that's nonsense. It doesn't mean anything, and you have to have underlined here. But if you write something like B star, right? And then you put a dot, then you're thinking, okay, that means something, because we recognize that as a regular expression, any number of B's followed by 1/8. But a star AB means nothing. You gotta get a dot between the A or B or a plus or, things like that. And then you're thinking, star, how can you start with star? You need a letter, then you put the star. So that's how things go. Now, since the set of all strings based on T is countable, it follows that the set of all regular expressions is also countable, because this is true. And then since we only have a countable number of regular expressions, the total number of regular languages will be countable. So you're thinking, how do you know that? Well, every language that is regular can be described by a regular expression. And sometimes two regular expressions describe the same language. So the set of regular languages is smaller than the set of, regular expression. And the set of regular expression is smaller than the set of all strings. And this is countable, set of all strings, because a string is, a finite sequence of things from there, but not every stupid finite sequence will produce a language. So you're thinking, okay. So you have this tree level, and then you say, okay, finally, the set of all languages on AB is uncountable. That was one of the first theorem. The second theorem improved. And so there must exist non-regular languages. And you're thinking, okay, I believe you, but I would like to see one, right? And now, just like somebody is saying, like with Cantor, they say like, Cantor, this is why Cantor was misunderstood. It's like, Cantor, we don't like your stupid proof, Not only did Cantor prove that they were irrational numbers, because they knew that before, Cantor proved that they were transcendental numbers. So you're thinking, Professor, anybody knows what transcendental number is? This is your chance to become famous, right? All right, you could write if you know, but I'll give you a second chance, So we will prove now, give several concrete examples of non-regular languages. And so what I was saying, Cantor did not only prove regular that there exist irrational numbers, he proved there exist transcendental numbers. What that means is that things like square root of 2, right, square root of 3 and so on, or square root of 2 plus square root of 3, or cube root of 7 minus 7th root of 18 and so on, all of those were countable. And he's like, really? And they are called algebraic numbers. So Cantor proved that the set of algebraic numbers was countable, and that means there are things that are not the solutions of an algebraic equation with integer coefficient. And then he's like, wow. And then somebody says, okay, give us one. And he couldn't give anybody one. But there was a guy, his name was Hermite. He said, hey, okay, give me a little time. And Hermite, and that's where you get operations for matrices. Hermite actually proved that E was transcendental, that E is not the solution of any algebraic equation with integer coefficient, and then he later on proved that pi was transcendental. So it's like A, E, and pi. But there are things like gamma. So you're thinking, what is gamma? Well, gamma is this constant, limit. So I think you need to know these kinds of things. That's why I'm mentioning it. Limit as n tends to infinity of 1 upon 1 plus 1 upon 2 plus 1 upon 3 plus etc. lots more plus 1 upon n minus ln of n. Right? So Cantor proved that this guy here, right? So you're thinking, well, Euler, my favorite mathematician, he proved that this number exists. It's 0.5 something or whatever, 0.577, God knows what else. I don't remember more digits. And it's called gamma. So this is gamma. And then nobody up to now knows if this is, transcendental or not. So, what can you do? So, I guess, I didn't write this nice here, 1 upon n. I want you to see like that. Okay. And then this is minus ln n, right? Okay, so it is always good to get a concrete example of something that is transcendental, and E and pi are, but we don't know about this crazy number. But this number exists, right? And as I said, when you do calculus, they might have told you. So here is a specific example of a non-regular language. And this one, remember we said, this is not A star, B star. What is A star, B star? So, and the reason this is not A star, B star is because A star, B star, this is any number of A's followed by any number of B's. But this one, they have to match. So this is not equal to that. So you're thinking, oh, okay, I see. Just because you got a star doesn't mean you're matching the number of A's and the number of B. You just have to have all your A's in front and then followed by all your B's. A to the K, B to the L, right? So, good. Now, it's 2:59. I got 15 minutes to prove this crazy thing, and then I will let you go because this is ugly. It's like, I don't know, does anybody like square root of 3 and square root of 2 proofs? I mean, they're all, terrible. And then if you want something really bad, look at Hermite's proof that that pi. The pi is the worst one. Ease was half easy, but pi, to prove that pi is transcendental, is horrible. And I had to do it for my math senior seminar, right? Prove pi and E are transcendental. That was the topic I chose, so I did it. But at the end, I was like, okay, praise the Lord, So those are hard, horrible things. And I had to do it, not only do it, but I had to do it within my time, right? So it was not easy, but we did get an hour. But I struggled. So because these things are difficult. Now, here is the question. This language AL1, A to the K, B to the K is non-regular. Why is that so? So you do the same thing you do when you say square root of 2. You say, suppose L1 is regular, and then you're going to get a contradiction. Then we can find a lambda free NFA such that L of M1 is equal to L1 by theorem 5. And then let N be the number of states in M1 and consider the string A to the N, B to the N. Now, this example 1 is so important because every test in test number 2 has a proof like this. And that's basically your one proof in test number 2. It's number 6 again, I put it because I don't want to show you the proof first. And you're thinking, oh, Professor, don't bring that. I have no choice. The accreditation people says you must test them on this stupid thing. So I say, okay. Since A to the N, B to the N is member of L1, M1 will accept A to the N, B to the N. Also, since it takes N1 plus 1 state to process A to the N, the acceptance track of ADs must have a loop as shown below. So you're thinking, okay, I don't know what you're talking about, but here is the thing. Just like we were doing that thing with, let me show you back here again. We are doing that thing with X, Y, and Z. The X was here, the Y was that, and the Z was here. Well, the same way we are doing here. This is the A to the I. So the first I things you get, and then you go wrong, and then you get something in a loop here, right? But they're all A's, right? So you're thinking, okay, you have to have a loop. Why? Because A to the N plus 1, A to the N, it from here all the way up to here. So let's stop here. But this is accepting. From here to here, you will have N plus 1 states because it's A little a to the capital N. So if you have a string of length 10, it needs 11 states to process it. If you have a string of length capital N, you need N plus 1 state to process it. And so you must repeat the state, and that's how you get a loop. Now, the loop could be anywhere in the middle, at the beginning, at the end, but it has to have a loop because you can't put N plus 1 things and they're all different when you only have N different states. So you have to have a loop, you have to repeat. So you get your loop. And let me make it nicer. I hate that loop. It didn't come out nice. So you go from here to here and you go like that. That's your loop, right? Okay. So now, if we skip the loop, we will see that M1 accepts this string, A to the I, right? And then you skip that loop, and this is A to the N minus J, B to the N, which is A to the N minus J minus I. Remember, I and J are you go until something repeats itself for the first time. And that's the I when it goes, and then when it goes around and comes back to I, that's QJ. So these two are equal. Right? And this is I, Okay, so then you're like, okay, I didn't write that too nice. I hate to write it ugly because I took out the dot. So these two guys are equal. And that's why they are this whatever state here, that guy there, right? And then you say, since I is less than J, this guy is A to the N minus J minus I is not member of L1. So we have a contradiction because why? The machine is supposed to accept things that only L1 allows, and L1 has matching. And you're thinking, this is a contradiction because L of M1 is equal to L1, and M1 accepted something that was not matching. They had more B's than A's. You're thinking, therefore, L1 cannot be regular. You're thinking, therefore, if it can't be regular, you're non-regular. So you got that. Now, that is the easiest of these proofs. And I keep giving you more and more, the reason being to let you master it. And then if you do 5 exams, you will master it. If you do 2, you might not master it. But 5, I think you will master it. So now let us, look at this guy here, L2. So you're thinking, okay, what is your L2? L2 is you have more B's than A's. So you're thinking, wait. You have all your A's first, then all your B's, but the number of A's is less than or equal to the number of B's. Yes, that's what K less than or equal to M means. So you're thinking, okay, and you're claiming that guy is regular, is non-regular. I'm saying yes. And then I do the same thing again. And this is the thing, all these proofs are the same proof by contradiction. So as soon as you understand one, you should be able to understand the other. But each one is slightly different. And that's why I give you 3 or 4. So suppose L2 is regular, and then we are going to get a contradiction. Then we can find a lambda free and FA M2 such that this is so that the L of M2 is equal to it. Let n equal number of states in M2 and consider this string again, A to the n, B to the n. Now, it wouldn't be that every time, but in this case it is. Since A to the n, B to the n is member of L2, M2 will accept A to the n, B to the n, because it was designed for that. Also, since it takes n plus 1 states to process A to the n, any acceptance track of this must contain a loop as shown below. So you're thinking, Professor, you're saying the same thing here, except that you don't have this weird diagram, you have a nicer, simpler diagram. Yes, I'm saying the same thing exactly. But now I'm going to do something differently. The last time I skipped the loop. Now, if we write this loop twice, we will see that M2 accepts the string A to the I, that's this part, and then take this 2 times, so 1 time like that, and go around and come back. So the first time you went like that, and then you went 2 times, right? And you're thinking, okay, I went around 2 times. What does that do? Well, it will accept A to the I, that's this part, then A to the J minus I, that's the part in this loop, and then 2 times, you go around again, 1 more time, and then you do A to the n minus J, that's this part, and then from here to here is B to the n, right? And you're thinking, okay, I agree, that's what is the big deal about that? Well, when you add up these things, this will be A to the n plus J minus I times B to the n. You're thinking, so what's the big deal about that? But this guy is not member of there because the number of A's is not less than or equal to the number of B's. Because this is, you have n B's and you have n plus J minus I, and J is bigger than I. So you're thinking, you have more than n A's. And you're thinking, okay, this contradicts the fact that L of M2 is equal to L2. Hence, L2 cannot be regular. So L2 is, and then you're thinking, oh boy, this is horrible. I don't like this. Now, there's another one, and after this, I'll stop. Because, you can only take so much horrible things for one day, right? So we will stop here the next time, and let's do this, and then we'll quit. And we have 7 minutes more. Now, you're thinking, you know what? I thought, okay, suppose you have one letter, just A alone. Can you get non-regular languages there? And the answer is yes. You can get non-regular language on a single alphabet. So you're thinking, but that would be a strange alphabet. One letter you only have. Yes, but you could repeat it. And so it can give you an infinite number of strings. Lambda, A. And so if you want to say something, this is the funny part people don't realize. They always think, well, computer use binary, 0 or 1. You can't do anything with one letter. No, you can't. Because, if you want to say some words, you can say, like, okay, you have to have some blank space. So if you want to say something like, if you can make one sound, right? You can say, ah, and then you wait a little bit. And then you say, ah. So you say, ah, and then big pause, and then you say, ah. And you're thinking, so you said 2 things there. So all you need is something like a big pause. So you need like a space. And then, so you can get things like A, and then A, and then A, 4 A's in a row. And you're thinking, okay, and then that could mean something else. And then depending upon how you space out your words, right? And then you're thinking, okay, but you do need spacers. And so it turns out that without a spacer, you really can't do much, because you cannot be able to say different strings without a spacer. That's why blank space is always there, right? Now, that's why you need zeros in computers. So 0 can work as a character with blank space, and 0 can work also without blank space. 0 can serve as the blank space. That's the beauty of 0 and 1s. So you got 0 and 1s. That's the secret of the computer. And now we got to prove this. Now, what is this? This is like a to the 0, a to the 1, a to the 4, a to the 9, a to the 16. So you're thinking, suppose L3 is regular. Then we can find a lambda free NFA M3 such that L of M3 is equal to L3. So you are finding a machine to do this job. And because you assume it's regular. And of course, I'll get a contradiction. Let n be the number of states. Okay, so you're thinking, always you say n. But now, I have to consider a different string. Consider the string a to the n plus 1 squared, which is a to the n squared plus 2n plus 1. This is member of L3. It will be accepted by M3. So you're thinking, yeah. Also, since it takes 2n plus 2 states to process this last 2n plus 1 is, any acceptance track of this must have a loop as shown below. So where do I have my loop? I first take this part here, n squared. That's this here, right? And then I have 2n plus 1. So this is bigger than n plus 1. And so I must have a loop between here and here. Now, that, of course, will be accepted. And then you go and you get accepted here again. But here is the part. Now, if we skip this loop, something magical happens. Now, if we skip this loop, we will see that M3 accepts a string a to the n squared, a to the I, a to the 2n plus 1 minus g. So you're thinking, what is that? You work it out, it becomes a to the n squared 2n plus 1 minus g minus I. But n squared is less than this because this is the positive numbers. So n squared is less than this, and this number is g and I are both, small numbers because they are less than, 2n plus 1. So g minus I will be, smaller than 2n plus 1. And then this is less than n squared plus 2n plus 1 because it has this minus amount here. This is a positive number. And you're thinking, so it follows that this cannot be a perfect square because this is a perfect square and this is a perfect square. And these are consecutive. There is no perfect square between two consecutive squares. There is no perfect square between, say, 17 square and 18 square, because that's it. After 17 square, the next immediate guy is 18 square. So you can't get anything between. So you're thinking, okay, it's not a perfect square. And then you say, but this contradicts. This guy is not member of L3. But the M3 accepts it. And M3 is not supposed to accept it because L of M3 is equal to L3. Hence, L3 cannot be regular. You're thinking, man, I hate this stuff. But no, it is nice. So L3 is a non-regular language. The next time we come back, there is something called a pumping lemma we'll talk about. And then we'll get into something else. We'll get into what you call properties of non-regular language, right? So I have to stop here because it's 3.